Okay, we are also recording as well. So hi everyone, again welcome. That's the general information about the course today, and it would take us a few minutes. It's still quite important to go through them so you make sure that all these information are crystal clear to you at the beginning. Again, if you wanted to contact me, send an email with this subject box. My name is Hadi, Hajibeygi, and this is my email address where you can reach me with. So next, before we start the course, I'd like to introduce two gentlemen to you. And I wanted to see if any of you know any of them. If you know, unmute yourself and say, whom do you think the first one in the top is? Does anybody know?
Confucius?
Yeah. Who is the next one below him?
No.
This
Darcy?
One? Well, not that close.
Darwin.
No, but they look maybe very, very close. I mean, on those days, everybody looked maybe.
Darcy?
No, no, he's not Darcy.
Jules?
Very close. So it's Lord Kelvin. So the first thing I wanted to bring from Confucius is that unless you do stuff, you can't really learn. This is extremely important. Whatever I teach in your course of Flow in Porous Media, you can teach, you can learn, you can do exam with it, and you can pass, but it may not really remain with you. And it may be few weeks, if not months or years, you're going to forget what happened. So if you want to spend a fruitful period of your life on these subjects, please try to connect it with what you do every day and do it. And so if you know Flow in Porous Media, you want to brew coffee tomorrow, you do it better. Or you want to cook meals, you do better. When you know the concept of wettability and the surface tension, if you want to cook even, you need to know when to add oil, or if you don't add oils, or how would you cook better when you know wettability concept. So this is important to connect it to your life, so you become a person who knows Flow in Porous Media instead of mathematics of it, and be able to solve the problem when they are given in mathematical form to you. So it's extremely important to do stuff to understand them instead of see them or hear them or remember them. Second is that don't presume much that things are impossible to be done. And this gentleman, Lord Kelvin, who is quite famous, is known to have had a strong opinion that heavier than air flying objects are impossible. And in fact, in 1896, he refused to join Aeronautical Society because he was so stubborn that that could never happen. So airplanes wouldn't be able to be invented. This is something that you always think that it is impossible to have flow like that, or product, or have production in this way. Maybe this is not the way that we think about it, is the classical way we think about it is right. Maybe there should be another machinery or design that would allow this to happen. And we have done that in the history of human beings. And I think there will be a lot more to come in the future as well. So this is extremely important. You, as scientists, as students, researchers, develop this skill that critically look at everything in your surroundings and try to assume that things could happen all, differently. It's not always the case that we should do life the way that we are doing today, or the Darcy law that I'm going to teach in a couple of minutes. It's around 150 years or so. It has been the way that it has been like that so far. We haven't majorly changed it. So we are using it all the time. And there is a time that it comes to you and you would say, when is it that I'm going to revisit all these type of concepts? And I guess there should be, if you don't ask yourself this question, you may not come up with anything like that as well. So try to be critical. And that's why I would like to really have you here with me with these kind of couple of weeks that we are going to have together to be sharp, focused, and listen to the story and see if it makes sense. And if it doesn't, just fix it then. And this is you who needs to fix it. And you have 9-month master thesis project next year. You can start to find out where your interests are. So with that, we are looking at porous media, obviously, in this class, because the porous materials are everywhere, and the subject of our research, the subsurface formations, are also porous. And we are in this class very much interested on getting to the depth of the subsurface, staying still at the crust level, still between 1 to 5 kilometers or so, not that more, and be able to see these layers. How can we find good utilizations for all these subsurface layers? And there are different utilizations about them. You could do a lot of engineering processes for providing economic and welfare, prosperity to the society, but this is extremely important also as we are living on this planet. So we need to learn about what planet are we living in, and this is our home. So either curiosity-driven or business-driven, market-driven, or climate-driven, or any concern-driven, this is the first study that anybody would look like to have, which is to know where we all live, and this is planet Earth. So we are focusing on that, and we're trying to see if we can take pieces of it and focus on different, for example, part of it, and study different subjects or different pieces of this entire geosystem. And we can look at it at different scales, obviously, as well. So the formations, geological formations, are porous. So we are interested in porous media, and obviously all the stuff that we do in these sort of things are related to flow, either geothermal storage or production of hydrocarbons or other deep water, underground water resources as well. So this is how we get into this business. So to rule the subsurface, it's the need to learn about flowing porous media, and that's really necessary for us. And it's, again, don't look at it as a course, take it as a skill that you need to develop and become an engineer who goes to work or proceeds with academic career would know and have a feeling about what the flow really is in porous media. What's the concepts of it? How can we model and understand and engineer it? The end of the course, you would be able to really understand why these processes happen in a formation. In a subsurface formation, we have started to inject gas from one side of it, and then we are producing oil from the other side. And what we see is that the injection and production, or the evolution of the second phase into this subsurface, is not a kind of, we wouldn't expect it this way if we didn't know flow in porous media and the concept and the quantities related to it. So that's quite important. Now we go next is that there are many applications. The science you learn in this course can be used in many other applications too. But we stay focused on reservoir engineering part. We stay focused on things that are in the subsurface formations. We inject, produce, or we are trying to do some utilization of the subsurface for energy, climate, environment, and water resources type of activities. Especially energy, which is this track about is energy, GeoEnergy Engineering. So you would get acquainted with hydrocarbons, with geothermal, with energy storage, with CO2 storage, and other activities like those. But nevertheless, there are a lot of other applications where the knowledge of this quantitative knowledge of this flow in porous media would help you understand the process and be able to impact those industries or those communities as well. With that, that's the course that we have this year with each other. Most of this part is going to be focused about single phase flow. So that's what we are going to do mainly in this course. So we start with understanding the properties of porous materials, quantifying their permeability, porosity, and understanding how we can do experiments to measure them, quantify them? How can we do modeling? And I hope that with the geophysics part, you would also understand how geophysical monitoring would help us to quantify some characteristics of the subsurface as well. Then we move forward after the properties to flow, to dynamics, to understand what's the Darcy's law, what's the flow system, how a flow governs. Is it laminar, turbulent? I mean, not laminar. Initial forces are important, and if so, how appropriately we could write the governing equations describing the balance equation, conservation laws in our porous system. Then we move on to upscaling, diffusion, dispersion in the porous systems, and finally we end the lecture with this part that I teach on multi-phase flow properties. So we end up with multi-phase flow and only about the introduction of it, just concepts about it, about capillary pressure, about relative permeability. These two concepts will be introduced only, and we will practice a little bit about it. You have the next lecture, entire course about multi-phase flow, which would cover a lot more comprehensive materials than these two subjects. This is the schedule of the course. I'm going to just submit it in the Blackboard in the bright space, but you're going to also see it in this video as well later on. So that would be the lecture of today, and tomorrow will be mainly about Darcy's law and potential. There will be a practical session next week. Kishan will do that. And this will be about practicing of what we are going to cover today and tomorrow. I hope with this online education we can cover as planned, but if necessary, I can always record you stuff that you could watch, and then we can have discussion hour at the beginning of our practical session as well. In that case, it would really make it more convenient to make sure everything is covered. If some questions are still remaining, please do let me know. So if I see that all of you have the same question, or many of you, then I can record 10-minute video and describe that specific question so that everybody else can also watch it too. The lecture Zoom meeting ID would stay constant through the entire quarter for my part. So this is the lecture ID that you use today. Please just save it somewhere with the same password that I can't really release it here. Then you just use it and connect to the course all the time. And please remember, one of you create the WhatsApp group of the course, so then add me, so that in that case, if someone is left out, I can text them and make sure everybody is on board. So with that, there are textbooks that are available also online, some of them. Please do read some books, especially the highlighted one is quite nice. Also, there are lecture slides, assignments, and many handouts that I can release, but it would be really important and helpful and useful if you at least go through a textbook as well, because there are so many descriptions that in writing we could also learn, and that would be quite important to read those stuff as well. And there are exams, assignments, assessments, laboratory. One very important aspect of my part of the course is that you're going to have a laboratory experiments. You're going to do that in groups and then write a report. Every year I'll describe exactly the procedure to submit your reports. This year as well, when the time comes, I'm going to tell you about it. Remember, you need to submit all the assignments and you need to get 50% of them, including a lab report, in order to be able to sit in the final exam. For my part and for Dennis and for Kay's part as well. So it's just 50%. It needs to be achieved in all of these activities before you can even sit for the exam. And as I started this general notes, please think beyond the course, question everything, try to see if you can really make sense about what we are covering in our course. So that's quite an important subject, and this is very important that you stay attentive to your course. And I'm trying to see if I can find Zoom. Yes, I found it. So I am going to now Okay, so with that introduction, I am going to now continue with the course. And the first lecture that we have today and tomorrow is quite the backbone of everything that we cover in this course, which is about Darcy's law. And that's quite an important subject, and it forms the basis of whatever we cover in this course. So the whole story would have different aspects. We introduced the concept of representative elementary volume. Then we will discuss about what parameters can be used in order to quantify the properties of porous materials. And then we start to govern equations because we would like to describe their dynamic properties and the processes in them, so to engineer them appropriately. So we start with porous media. I have already said that geological formations are porous, but do you have any specific interesting item in your mind that I haven't mentioned and noticed? I mean, describe it, and it is porous. Can one of you just mention as one porous material I haven't really mentioned so far? That would be quite fun.
Porcelain.
What?
Porcelain.
What is it?
And I mean porcelain. I mean
can you describe it? I can't hear you.
I mean, porcelain, the material you can make vases out of.
Oh, right.
Like
okay.
Porcelain vases.
Okay. Yeah. Very nice. Yeah. I just okay. Jihang, was it you who?
Yeah.
Okay. Jifan. Sorry. Yeah. Okay. Good. Any other? There are so many examples as well in your yeah, sure, sponge. And you see even my clothes, my body, I mean your body too. Many stuff around us are all porous, and there are processes happening inside them that can be also looked at and be engineered in order to be optimized or to understand and design them appropriately. So there are many examples. Rocks are porous, of course, sand as well, if you pack them in one kind of container. Sponge, underground formations, food industry has a lot of examples. In fact, there are many research activities happening in designing the right coffee cups or coffee machines so that the steam, when it goes through the coffee, it would get at the end of the process a good taste and get the right diffusion and the flow rate as well. So you don't want to wait too long for your coffee to be brewed. At the same time, you don't want to have a tasteless coffee too. So there are extremely active business around this subject, with drawing also of food as well. Apple or the dried fruits that you get in supermarkets. They are also dried, which means evaporated water from the porous structure of food. And the right way of this evaporation and drying process would keep the taste, nutritions, and quality of your dried food also maintained. So that's why they taste differently, and some are higher quality, some are not as high quality as well. And also rocks and reservoirs, geological formations, of course, too. Many applications are there. Energy production and storage, environmental activities for CO2, for example, storage, water resource management as well. Deep underground water resources are in porous rocks. And there are many challenges, like scale heterogeneity, coupled processes of the physics that are there, uncertainty, data, and responsible use of them. They're all the kind of things that will be clear to you more and more as we proceed in this master track. It's very important to know at the end of the day, what we are interested in is that there is a flow happening in that subsurface formation. For all these applications, the key aspect is there is a fluid that flows, either CO2, either water for geothermal, either hydrocarbon, either hydrogen or green gas or whatever, as like Alex said that he has worked on aquifer thermal storage. Again, there is a water storage somewhere, and then you heat it up. So there is a fluid that can flow and can be used for utilization of for energy, environment, and other aspects. So that's why we study this flow in porous medium. As I said, if you go under the ground, you will see from the shallow surface, you get deeper and deeper under the ground. You see that there are different formations, and you can utilize them for different purposes as well. Sometimes when we drill wells and we drill something to interfere and do our engineering process, we can also collect some rock samples like these samples here. And then we can image them, study them, experiment with them as well to understand and characterize what is in the subsurface. Energy storage is also another subject. So I have a QR code of a 4-minute long video I recently have recorded about one aspect of it. The whole concept is that you have renewable energy, you want to store them in large scales. And if you convert them to green gas, like hydrogen or green methane, or like heat that was also mentioned by Alex as well, or pumped hydro and other compressed air as well. There are alternatives that they are different between the capacities they hold and the storage time, the time that it takes to reclaim them at the surface. And then you can store, because you can store them in the subsurface because there are giant capacities, a lot, major, big reservoirs.
Can I ask a question?
Of course, please. Please.
The pumped hydro, is that in the subsurface, or is it?
No, the pumped hydro is actually, you actually do that not in the subsurface. There are actually not for energy. For energy storage, pumped hydro is not a subsurface-based energy storage. You just pump in the lower, let's say, level of the mountain to the higher mountain water. Like this is some companies in Switzerland have done that as well. And then you need mountainous, let's say, landscape, and then you do that. That's absolutely not subsurface related. Compressed air, hydrogen, and green methane are subsurface-based heat. If you do aquifer-based heat, then you need subsurface. If you do it differently, then differently. Yeah, very good. And this is this video that I have recorded recently is 4 minutes long. It's about using salt caverns for hydrogen. But I hope that in the future also I record more and more so it becomes more clear as well. So if you had time, 4 minutes, please have a look at it as well. Then we go to geothermal, which is if you go deep to the subsurface, you see that the temperature of the earth increases all the way to the core, but we don't go that far. We stay within a few kilometers in the surface. And then you have, based on the location that you are, you see different gradients for increase of the temperature if you go deep. Now, tomorrow, a colleague of us who works on geothermal, Maren Breme, who also will teach at the end of this course as well about geothermal stuff or fluid chemistry. She's going to give a live webinar tomorrow at this address. So it's going to be on YouTube and you're going to watch it also later, but that would be also nice to just get a good grasp of what is it about as well. So geothermal would be another application, and we are doing it in TU Delft as well. As you see, this is the TU Delft subsurface formation. That's how the heterogeneity of the system looks like. Green, red shows high value, blue shows low value. I'm showing the porosity and permeability here. I think it's porosity. And then here you can actually simulate or model what the dynamics of the flow in this system looks like. Unfortunately, the video does not play, but it's not really important as well. Anyhow, that's all about these porous systems. And now we need to learn about the dynamics. Obviously, we need to look at them and try to characterize them. And these porous materials in the subsurface geological formations are different in terms of mineralogy as well. Grains are different, rocks are different. And there are geologists in the class who could speak about this subject a lot more in detail, but I wanted just to open up this topic that rocks are different. There can be sandstone, there can be limestone, they can be different and with different mineralogy and obviously different properties for flow as well. That comes later about wettability, contact angles, and capillary pressure, or the concepts as well. We can do a lot of different ways to image them. So you can have many ways and instruments and technologies to image and characterize your rock. You can do microscope, optical way, or do CT or micro CT as well. And these also there is a webinar used to be in about 3 months ago. A colleague of ours, Firle, gave an overview of what is the state of the art of imaging porous rocks with CT and micro CT scan. So that would be extremely also nice if you had half an hour to also watch that webinar too. And now, as you see, as I'm proceeding, I give you some references that are modern. So I belong to some generation that YouTube links work, Instagram works for them, Facebook, LinkedIn, and other pages as well. So I would like to have you go through this half an hour video of Verile to go through what's the advancement there. Of course, there are many other materials, but it would be fun as well. So if you are in, I don't know, Sunday evening, you just feel that you need to do something fun, you don't know what, that's exactly what you should do. Watch these videos. Okay, then I would feel very much happy that I am giving you some fun schedule to do as well. So we characterize, we look at them, but then now looking at them is not enough. We need to come up with some sort of concept to describe them and study them. And I'm going to give you a break in 5 minutes before I just describe and just open this. First, I will describe this, the way that we study porous material, and then you're going to have a couple of minutes break. If we want to study porous media, the very first question we need to answer is at what scale we would like to study them. What's the appropriate scale to look at them? As I said, even to look at them with microscope, with CT, micro CT, with field geophysical observations, they are all different ways of looking at the same system. We have different eyes, different eyeglasses, different filters, and scale and resolutions to look at the same species. And that's very important, especially in flow dynamics modeling, to know at what scale do we want to understand the process. And this is really something that is essential and important, because that would describe how we could appropriately apply the physics of the nature in order to understand the process that we want to understand. So this is important for us to look at the variety of the scale that we have in the subsurface, from kilometers and beyond, all the way to molecular level. And all of them are important, and they are being pursued and being studied. What we focus in this course is that very practical scale, this scale of continuum scale that we called it Darcy's scale 2. We look at this core and above, and we take all the properties from below, from a more higher resolution, as functions and quantities described for us, like permeability, capillary pressure, relative permeability, to do more engineering look into the process. So we focus on this. In this scale, this is called porous scale, which is micro scale. There is another video, a very nice video, again, half an hour's scale video, to go through what's the state-of-the-art process of this scale modeling. We don't do porous scale modeling. We do continuum and Darcy scale and above. and this is quite important. There is a course next year, subsurface storage, that I teach, and I have with Leila, we have one lecture about the porous scale modeling as well. So until then, you don't have to wait, but it would be really fun video to watch. It's extremely nice and valuable. I don't want to repeat the story that is already being available already to you. And now I'm going to focus on this and try to understand how can we describe this system? How can we model, describe the flow process at Darcy scale, which is extremely important for engineering applications. The first concept that we do before the break is the concept of REV, which means you want to do continuum scale. Okay, fine, do continuum scale, which means things are in continuum. They're not as discrete and abruptly changing as in lower resolutions. Then you need to give me an REV, a representative scale, a representative volume, so that over which I can describe my process properties. So REV is small, at the same time big enough that if you want to take, for example, this white to say, I want to know how much of my porous material is void. If you take this big rectangular box window and go through this, you're not going to get one value for your property, let's say porosity here. And so this is not going to be the right one, because the porosity before, it's 0 because it happened that you put your window on a grain, and next you happen to put your box in a non-grain, in a fluid part of the media. So that's not a representative window. You need to make it larger so that it averages out the variations. So you start to increase and increase your size, and you finally get to the scale at which, when you see the variations, when the system is small, when your window is small, you see large variations, but when you make it bigger, 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 variations average out, and you end up with one quantity about, let's say, porosity. So you say, I have a big enough window that when I change in my whole sample, I report the same porosity. That's the principle behind this REV. For density, it works beautifully, because density can be seen in bulk material, in the atmospheric places. So you can just go above a value, then you can say, I can describe my density. With porous structures, especially underground porous structures, which are extremely complex, there is a big question that I have mentioned down in here. And that question is, can we really reach to a scale at which we can say this is REV? Can we have really a scale at which, if we screen our sample, we can say that's really the porosity? And this has been debated over. And this is something that you need to always think about. The concept of REV, that is, I say porosity is this much. It is something that comes with some sort of an averaged look into the subsurface microstructure. Okay, now I come to the point that I can define properties. I am not looking at the nanoscale, I'm not looking at very tiny scale. I am at the box window look that actually can represent a value. With that REV, I can say, this is my porosity, this is my permeability, this is my density of the fluid, this is the wettability. These are the properties I would like to describe. All of them will be known to you just in a couple of minutes and hours and weeks through the course. With this REV, there are texts, there are interesting stuff that you can say that density of the fluid is defined also on REV. You can say the density is this. If you go to molecular scale, then you are going to have a molecule comes, goes, then you have a lot of variations. But if you come to continuum scale, then you see this is density of water at that temperature, and pressure is given by that value. So this is the scale that allows us, this is the to describe our properties at continuum scale. Now, with this philosophy, I am going to now start to quantify the properties, to see what properties are necessary to help us understand and characterize flow in porous media. At the end of the day, remember, REV is a kind of a useful concept. It allows us to do a lot of engineering processes conveniently. Okay, so with that, I am going to start with porosity, and I would like to give you a 10-minute break so that we can resume in about. Okay, so we are back. We are now trying to start, after knowing the representative elementary volume, to quantify our porous material. Now, the first quantity that is needed to quantify any porous material is actually porosity. Porosity is the amount of void space a material has, and since it has void space, we call it porous. So the two terms come side by side. We could always, I mean, if I was teaching in person, I typically create a porous sample for you. If you see me, do you see me? While this screen share, if you see full screen of my slides, you could escape, and then my video should appear somewhere in your screen too. If
yes, we see you.
We see, okay, fabulous. So I have taken a syringe that every one of you could buy in the town, and I have taken some sand, like beach sand, and filled this tube with it. Now now that it is now in a container and packed, this is a porous material. The grains inside this tube are packed on top of each other, and the void space between them forms the connected void space that allows fluid to flow. The first thing I would like to know about this is what's the percentage of the void space of this porous sample? What's the porosity of it? And we call it with the Greek letter phi.
Around 50% maybe.
Yeah. What, Pele?
Around 50% maybe.
50%. Well, that's quite to the very high estimate. It's in this, the sample I am holding in my hand has much less. I would say maybe 25% or so. Okay. But the thing is that we need to know about it. So we need to check if Pele is right or I am right, or what's the real value. How would we check that? Imagine I want to check the porosity of this sample right in my hand. How would I check this?
Masses and volumes.
Mass and volume. Who was that?
That was me, René.
René. What's the mass? How do we measure mass?
By weighing it.
We weight it. So in a way, empty tube, we weight it. After filled with the sand, we weight it. And we know the difference which must be for the sand. So we know the weight of the sand. Then is it enough for porosity calculation?
Well, we would also need the density of the sand and
so
volume.
Then we would say that with the density of the sand, with this type of rock, then we know that this sand, if it wanted to fill entire space solidly with no porous space in between, it would have this much volume, because density is mass divided by volume. But now we see what's the difference between the real volume that we observe and the volume that the density would give us. That would give us the void space, right? That's approach one, and that's actually being practiced in some laboratories too. What other ways I could do in order to do this calculation? Imagine I don't know the density of this grain now.
You could fill it up with you can measure how much water you've put in.
Absolutely right. It was Ewald. Is that you speaking? Yes? Okay, so that's I found it in our kitchen. So I hope that everything in the house is in good order after my teaching of this quarter online. Now, what I can do is that I can feel water here and see how much water I am adding until, let's say I can fill up the water, a given amount of water, let's say 20 milliliters of water, add it here and see where does it stand in the mark, in the label. If I add 20 milliliter of water, But then I look at this grades and I see instead of 20, it is 25. It means 5 milliliter is the volume of the grains that are taking space here, and water couldn't go there. So then this way I can find what's the volume of the grain and then find what's the porosity, right? Because I can, in fact, even from here, I can read what's the volume. It's 15 milliliters here, 15 milliliters. So if I find the grains are 10 milliliters, then I know 5 milliliters are void space, which means porosity is 1/3, about 33%. Okay, so I need to know the amount of water I am adding here. So I add 10 milliliters, then I look at it and say, oh, it is still. So I add 20 milliliters and I find that it is at 25. Then I say, oh, 5 milliliters is the grain space. That's precisely what you would do in your kitchen and in your laboratory and everywhere else as well. And this is not rocket science. It's rock science. It's easy, convenient. If you just think about how could I do that? So we just try to ask too many questions from Mr. Darcy. How would you do this? How would you? No, you can do better. So Darcy would come and say, hey, Ewald, you can do better than I did 150 years ago. That's precisely the experience of science. So here you can do that. I wanted to order you these syringes, and they were about 100 euros. So I tried to see how I can find, but I'm gonna just prepare a pack for you so you get it at your home address or come and pick it up at the university campus to do some science experience like the time you were in daycare and then later in basis school. Go back again to that stage because the science today is still depending on these sort of experiences. So I can fill up some water. I didn't have the second syringe in the house. I didn't find. So then now I can fill some water here without knowing how much water I'm adding. So by the way, this is now I added water. There are bubbles, blub, 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 coming out because the air in here is now being displaced with water. And air is light, so it comes up. And that's exactly gravity based process, right? So I'm trying to wait until the whole sample is wet. And that would be, if I knew how much water I have added here, then I could measure the porosity. I don't know. So I can't do that, okay? So how else we could do this measuring of permeability? Porosity. There's so many. I could use a lot of schemes, absolutely right. So I could do different methods. Definitely, let's go through them quickly in a couple of minutes. There are direct methods that are, if you are given a rock, which is not like this sand, then you need to really crush it and make it the grain, weight it, and do these sort of things. Obviously, the problem with that approach is that you would find your total porosity, and at the end, you don't have your sample again because it's being damaged. So I rather, if I go to an exam and testing what's the porosity of this, the person who want to do that doesn't really damage my sample too. There are other approaches. You saw the picture of the microscopes. You could do a scan of it. You can look with microscope, a thin layer section of your sample and try to find where the void volume is, and so measure your porosity.
There will be different porosities, right?
That is absolutely right. Absolutely, Ilara. Absolutely right. The thing is that even with the crushing the sample, you will have error. But here, with a cross section of the optical based way, there are many sources of error. One is that depending on which cross section you look at, you may find different porosity across the sample. Creating 2D, and then you don't know exactly are these pores connected, or it's a cavity, a void volume somewhere isolated. Would that be what you wanted to say, Ilara, or others? Apps, that's precisely correct. And so it's a two-dimensional cross-section for a 3D complex thing. But That's one way that sometimes we try to analyze and understand the cross-section, and then we do that. And we may do that for different cross-sections, but we know that this is not really a full representative of 3D, unless we know that every grain is, they are really well sorted and there is no heterogeneity in the cross-section in the vertical direction if we are doing some cross-sections horizontally. But that remains absolutely a valid point related to that optical approach. Alternatively, we could, I added water here. I could do differently. I could take my sample here. I could take my dry sample, weight it, put it in a tank of water, and then wait for some time, or even shake it like this, and then take the wet sample out and weight it again. Now I have a question. What would be the difference of the weight be related to? Ilara, since you have said already with the optical one, you found a big drawback about it. So how can you now say, what would be the difference between these 22.5 and 20 grams? What would be the weight of this due to?
The water in the connected pore space.
Precisely. Excellent. Absolutely. So the water that is inside the pore spaces of this sample weighs 2.5 grams. We know the density of water, right? Because it's simpler than density of this grain. Water is about 1,000, an SI unit, kilogram per cubic meter. So if I take my 2.5 grams divided with density of water, I get the volume of water that went inside the pore space. So I get the porosity this way, because I know the volume divided by the total volume of the entire sample, which is cylindrical, so it's cross-section times the vertical dimension. That's another approach. We did it reverse here, because I have a sand pack, it's loose. But if you had a rock, it was solid, you can put that. So now I need one other brave student to volunteer and give me a big drawback about using this.
It's very hard to completely saturate your sample.
Who was the speaker?
Rene.
Rene, okay. Rene, you don't have your camera today with us, but you are actively following us.
It'll be there next time.
Okay. Or send us a photo of you, please, so that I know how you look like.
I'll try.
Okay, precisely. So the thing is that, first of all, you would assume water would go inside the sample and would take air out. Maybe it doesn't. Maybe it doesn't like the sample. Maybe the sample is not water wet. Maybe it is non-water wet. I wanted to mention the other fluids, but I rather wait for a bit longer. So then it doesn't, hey, water, go away, I don't like you. No, don't invade my pore spaces. Yeah, we have these minerals. They don't like water, unfortunately, or fortunately. They like oily materials, gas more. The other thing is, you need to make sure that the water has been able to go through all the pores, and there are not little bubbles of air that stay there. Shh, Tom, don't say anything. Water is coming, taking us out. They're just hidden somewhere in the pore. We call them trapped non-wetting phase. They're trapped like bubbles there, and they don't really move, and they are just silent, and say if they are escaping the water, they will survive this experiment. And that's it. So you still have errors, like the other one that Ilara found the mistake, or the error for the cross-section based image optical approach. Here we have also approximations too, or errors as well. So there's no perfect way in so far, actually, to say so, to see how do we measure the porosity.
Would you be able to improve it by flushing your sample with CO2, for example?
Flushing, you could actually, gas-based approaches will come in a few slides. Absolutely, gas would penetrate a lot better than, let's say, water. So there are other approaches, like imbibition approaches, And then instead of putting it, for example, in the tank of water, you put it in the tank of the wetting fluid. If it wets oil better, so you put it in the tank of oil. You don't have to put it in the tank of water. There are other approaches, mercury injection, and please look into them and study them. I can't go through all these processes, but these are all important processes for us to find and characterize the porosity of a material. Now, there is another way for us to find out the porosity of material. And that's basically using our intelligence a little bit more by putting a sample like this. This is our rock sample in a container in this vessel. And we have a pressure here at the P1. So we open up the valve here in below here. So it will be filled with air at pressure 1. So at time 1, I know that it is P1 because I read it in this gauge P1. And I know my air has V1. It has volume 1. What's the volume of air in time 1 when this valve is closed? What would be the volume of air in the time 1 when that valve is closed? I need another person.
Would be the total.
Who is speaking?
No, this is Ren speaking.
Okay, Rens, go ahead, please.
So it would be the total volume of that space minus the volume of the solids.
Absolutely right. So V1 would be the volume of container, but the grains are not letting the air come, right? So minus the solid, volume of the solid part, or grain, or whatever you call it, right? Which is 1 minus porosity times the entire volume of the sample, instead of porosity of it, fraction of this. So that's the grain, the solid volume. Now, if I open this valve, what will happen? And I close this one. This air would start to also fill up container 2 as well. What will happen? So imagine I open up that valve. What would I see? Air would go to the vessel 2 as well. What do I see specifically in these pressure gauges?
The pressure would drop.
Would drop, absolutely. Because it was first high pressure, maybe high, a little bit high, some pressure that I would observe anyhow. And then I open that valve, it has more space to go, so the pressure would drop. Now I have a step 2, which is time step 2. I know that my system has new pressure P2, and the air has at V2 stage. Now I need to know what V2 is based on V1. Who would tell me that? Someone who has not spoken yet.
VC2.
Who is speaking?
And this is Lamp speaking.
Jilang, is that you?
Yeah.
Okay, go ahead. So what would I add to V1?
I think it's VC2.
Fantastic, excellent, precisely, correctly. What else? Absolutely right. That's all I can remember now. That's precisely what happens. So I add the V container 2. Now, ladies and gentlemen, boys and girls, we know from the law of physics of ideal gas. What do we know? P1 and V1 at constant temperature is proportional to what?
P2.
And
Exactly. Exactly.
P2, V2.
If temperature is constant. And we assume ideal gas. Or if it's also real gas, we assume that Z factor, the deviation, would also stay constant. It wouldn't change. So if PV is ZRT, Z also stays constant. So I equate the two and then I find the porosity. How? Details follows. So we know that the volume 1, this is volume 1, is container 1 minus the solid volume. I wrote solid volume as bulk B, which is total volume, minus pore volume. Because grain, I wrote it in the previous slide at VS, the solid volume. Solid volume is the total volume minus the pore volume. And the rest is exactly as we just discussed. P1 V1 is P2 V2. And then there are mathematics related to it. I put V1 here, and then this is P2. So this is a P final, which is P2. This is V2, and then it is P start, which is P1, and that's V1. With doing that, I can find what's my volume of the pore space. And then dividing volume of pore to the total volume, I find my porosity. Okay, porosity will be volume of pore divided by the total bulk volume. And that's it. So don't be distracted with these sort of mathematics, which is just simply rearranging the terms. The whole thing you need to know is what actually, or learn about this whole thing, is the discussion we just had here. And be able to say volume of the solid is volume of the entire bulk minus volume of the pore, because that is what you're after. You're after volume of the pore divided by volume of the total. So these are the actually processes that ideal gas law helps us, or gas law helps us find the porosity. And with gas, we may have higher chances of penetrating through the sample. Now, one thing I did not actually explain fully is, I don't know why I didn't. Okay, so I skipped 2 slides, I don't know why. Is that we did all these experiments for porosity to understand, but we need to make sure that we understand the porosity as well. When we find porous spaces of a material, there are 2 types of porous spaces. Some pores are connected and they make pathways for the flow to happen. Some pores might be totally isolated. Imagine, for example, maybe this is totally isolated. So we have interconnected pores, which create pathways for flow to happen. And we have non-interconnected cavities, void spaces that are just void, maybe because of chemistry, geochemistry that has happened, and they are not connected to anywhere. What is the porosity that is important for us in the fluid dynamics? Interconnected pores. Interconnected pores are those which would allow us, for example, to have flow in our sample. So whenever in this course I say porosity, I mean effective porosity, which is defined based on the interconnected pores, the volume of interconnected pores to the total volume. I leave those cavities, holes that are not connected at all as part of the inaccessible void space, which wouldn't really matter for us. So we speak about interconnected pores, those pores that allow fluid to happen. And then the story here happens, that the story that I said about how to measure porosity, if you do that for different type of rocks or sand, you get different values. You see, for example, unconsolidated rocks, these are not like these sort of things, they're not really compressed and kind of consolidated. You see much larger values, much bigger values, you see 0.2 or 20%, 40% for gravels, for sand, for others, for clays as well. Then you have consolidated the rocks, then you have different like sandstone, you see them between 5 to 30% with porosity. Shales, of course, are quite low with porosity. Yeah, crystalline rocks as well, densely. It's almost very, very little porosity. You could see them. These are the slides that you can go through. And this is the story that we covered all to see how we can measure porosity. Now we come to the next concept of permeability. And I have 10-15 minutes to start this and then hopefully finish it tomorrow. Now, porosity is the static property of my sample. I put some sort of a known value of water, then I can do some mathematics, find out 30% of this sand pack is porous. Or I do imbibition, I do a mercury injection, I do optical, I do a gas law, whatever I want to quantify and characterize this porosity. Now, there is the second parameter that is crucial here for us to quantify the dynamics of the flow in porous media is permeability. And let's go to some experience that Darcy had, Henry Darcy, in order to characterize water flow through supply of water to city. And he did some experiment and then formulated a very simple law that has been used since then. And he submits a report in that respect for that work that he did for distribution of the water and the filtering of it. So that's where you can also find the, I believe, French report. I don't think it's an English report there. Okay, so what's the deal here? Darcy put an experimental setup to measure how easy water can flow through this sand pack. And this is exactly what I hold in my hand today in different, of course, scale and different setting. I have sand here, and then I put water in here, and I can keep the level of the water constant by just little by little adding water to it. But I'm going to be lousy because I just want to give you the concept of it. I'm not going to connect it so the level of the water up in here stays constant. What I'm going to do is I have again stolen another piece of stuff from my kitchen, which is I am going to let the flow happen. And when I, take my hands off this sample, I would see that water would flow. Where am I? Do you see droplets? Do you see droplets?
Yes.
This is still also extremely high speed compared to what happens in the subsurface. So I have put water on this sample, and I see dirts of 8 years are coming out of this sample too. So you see that if I add water in it, you would see that water would drop off this through this. So water is flowing through this sample and exiting from the other side. Now the thing is, how could we quantify this dynamic process? This is exactly what Darcy did. The difference what he did is and what I am doing is that he kept the level of water here constant, and it's important to keep it constant. Here, when my water column, actually the water is flowing here, the column here drops as well. But since it's dropping little, I am actually fine. What we can do here is we can count how many seconds does it take until I lose 1 milliliter of water. How many seconds does it take to lose 1 milliliter of water in this sample? What would it give me?
Flow rate.
Flow rate. I would see what's the flow rate. Of course, I am being here quite I'm making approximations here because I need to keep this stuff here in constant level for the water head to stay constant. But just very approximately, I can say 1 milliliter of water takes X seconds, 50 seconds, 60 seconds to discharge. That gives me the flow rate. It gives me the Q. The volumetric flow rate is 1 milliliter per second, per 60 seconds, which means, for example, 1/60 would be the volumetric discharge rate of this sample. With knowing the flow rate, he started then to say, what could this flow rate possibly depend on? If I connect a pump in the top, I would see faster flow rate, right? So the first thing that he came up with is that if I have this sample that water is flowing through, I need to define potential, which is pressure, thermodynamic pressure, plus the hydrostatic one, the rho g h1. P plus rho g h is the potential at any given level compared to, relative to any reference gauge, any reference layer, level. Z will be defined then based on this to go upward. That's my axis Z. Then I see that I have H2 here, I have H1 here. Potential at the top is phi1, potential at the bottom is phi2, because it has P1, it has P2 here, and it is at level H1, and it is at level H2. Then he said, well, you know what? The discharge rate divided by the cross-section area would give you the velocity, the average velocity across this cross-section area. So across this cross-section area, you would get the average velocity through your sample. This velocity is called Darcy velocity. It's superficial, it's average velocity across the entire cross-section. Darcy said, phi1 minus phi2, phi1 minus phi2 are the driving, is the driving force for this flow to happen. If you increase pressure at the top, you would make it faster flow. And divided by length of your sample here, it would give you what would be the potential drop over the length of your sample. So it would give you for 1 meter of your sample, what would be the pressure drop. So per length, what is the potential drop? Mathematically, we can replace that by saying that it is gradient of the potential. Gradient, d phi dz. We can write it that way, which is phi at 1 minus 2 over L. Or to be more precise, it is minus d phi dz. That's the one below. Phi1 minus phi2 divided by L. If L is longer, but you keep the same phi1 and phi2, you're going to see slower velocity. That's correct. That's correct. If I create the same potential drop in very short distance, I can observe a lot of flux. Then he started to say, what would be the proportionality? What should I write here? Is this just equal? Or there are properties about the flow, the fluid, and the rock to consider? So he said, if I would have used honey instead of water, I would have observed slower flow. If I would have used more viscous fluid, I wouldn't see this speed. So then he said, the first thing to add is the viscosity, fluid part. Viscosity of the fluid will be in the denominator. If it is highly viscous, like honey, velocity would be smaller. Then he is left with putting the property of the rock here. The property of the rock is then defined as permeability. He says how easy rock allows you to flow. So is not resistance, is the inverse of resistance, is how permeable the rock, the porous material is, or how easy, or what's the capacity of your rock to transmit fluid. It's about how easy it is to flow. So if K is high, it means U is high as well. If viscosity is high, velocity will be low. If potential difference is higher over the same distance, your velocity will be higher. So permeability is the property of rock, of the porous material, and it's about how easy it allows flow to pass through its pore structures. And that's a rock property. Remember, this U is average U. So if you have a cross-section area of your porous materials with these grains there, so imagine these are grains, we have divided the total flux Q, we have divided Q by the total cross-section area to find the Darcy velocity. But we know that there are grains that would not let the flow happen. So in that case, the real water flow would be the flow across these void space, right? So water is actually flowing in faster speed. But since we just made an average over the total cross-section area and not just pore part of the cross-section area, we define this as average Darcy velocity. It's a kind of a superficial velocity. The real velocity of water inside the pores is higher, is the velocity of Darcy divided by porosity. Because that thing is Q divided by, then you have area A. This area is the total area, not the pore area. The pore, the white space here in my figure is actually where the real velocity of water really happens. But we are going to do average over the whole cross-section area of our sample, whole area, and not just pore area. So that's why we just call it Darcy velocity. So the real pore velocity is V, which is velocity of the Darcy divided by porosity. If porosity is 1, the two are equal. If porosity is 0.5, then water is actually flowing twice as fast as the cross-section based average velocity, which makes sense. Like imagine you have this velocity, this cross-section area, half of it has this velocity, the half is 0. Average would be this value, which is half. In all part of this course, we use Darcy velocity. We always work with this formula. And we always make the flow rate divided by the total cross-section area and not just the pore cross-section. That was just to clarify this. So a few notes about permeability before we close the lecture today. Permeability is the capacity of the rock to transmit fluid. Porosity is about what pore volumes are connected to each other. Permeability is more about how easy the flow can happen. And I can exactly measure it with what I just did for you. I have it now taken photo with the slides. So you see that I put your sands, and then I let the water column to drop a bit and then measure the time based on the clock here. Based on the clock here, you see the seconds and everything else was different when I had this 2 milliliter drop. Of course, I am making some assumption. You should keep the level of the water constant, but that's just back of the envelope, having a feeling about what that all is about. Then I find the velocity based on Darcy law. Say Q, discharge rate divided by the total cross-section area, is the velocity. I put the values here, potential difference, viscosity. These are all the practical. Also, we will practice about this a lot in this week. Viscosity, and then I find, based on the velocity that I have calculated, I find what the permeability should be. Potential difference, length, and all the kind of things. And I see, based on what I do in my calculations, I find permeability to be 6 Darcy. 6 Darcy is 5.9, 10 to power minus 12. 1 Darcy unit is 10 minus 12 square meter. Permeability K has the dimension of square meter or meter square. And if I do, I'm going to teach you tomorrow about how to model permeability and find the value of permeability with a flow in one tube and then changing it to complex geometries and then adding some experimental adjustments to it. The Kalman-Kozeny model that will be explained tomorrow actually gives me 25 Darcy. So I'm not, well, am I happy with this experiment that I did? If I do it, I call it I'm close, but if you want to be really careful, you may see that, yeah, it's not too close. But this is for more comprehensive way. You're going to do exactly the same experiment with more apparatus and more instruments in the laboratory during these courses to measure porosity and permeability of your sample. Okay, so that was just to give you a feeling that flow through the pores gives you flow in porous media, and this is exactly what Darcy did, and you're going to do, and we are going to do as well. It would allow us also do a lot of understanding of how easy or difficult the flow through the pores happen. Same would happen in the coffee as well. Huh? This is a coffee machine, the coffee brewer, which gets water in the top. You have coffee here, and then it takes 24 hours till all the coffee is brewed here. So they brew it over 24 hours and they sell it quite expensive somewhere. They call it in California, they call it Dutch coffee. So I had to try it myself too. And it was really like a flow in porous media when you drink it. You feel Darcy and all the kind of people around on it, okay? So these are the ranges of the permeabilities that you see in different rocks. Remember, 1 Darcy is 10⁻12. Viscosity is Pascal second, is 1,000 centipoise. Also, there are some sort of units that are being used, centipoise and Darcy, just to know the relationships. I am very much pro standard unit. They are convenient, they are easy, they are just comprehensive. But a unit of Darcy is being used a lot because permeability of rocks are quite low, and they are in the order of 10⁻12 and below. So that's a lot more convenient to write, I don't know, 1 microdarcy than writing 10⁻19, right? 12 and 618, sorry. So it would be just more convenient. Or here, Darcy, it would be 10⁻12, right? So these are the things, or millidarcy, 10⁻15. Nano Darcy, the nano is -9 and Darcy is -12 itself. So it's 21, right? So these are really low values that you see here in real life. So with that, I'd like to just end with this last slide to say that with the now knowing U or velocity across porous sample cross section is proportional to the permeability over viscosity times the phi1 minus phi2 over L. That is called Darcy's law. And that allows us understand a lot of processes, especially, for example, to understand the injection of gas that I showed at the beginning of the course. See why gas evolves this way. See, gas could not penetrate through this part because there is a blue part. There is a low value of permeability here. So especially this part, permeability is very low. So it is actually escaping itself from this part and then entering this red part, which is very, very high perm. So it likes that region very much, and then channeling to this part as well and reaching itself towards the production line. And the plot of permeability in logarithmic scale would help you understand this. Yeah, and you can also, with these study now, you can place your wells appropriately so to optimize your production or injection or storage. And at the same time, you could also intervene with it and change permeability by, let's say, fracturing, by increasing the fluid pressure to crack the rock so it allows more fluid to go through. So this is the fracturing thing that you do to alter the permeability of the rock. So with that, I'd like to just finish the lecture of today. and review that we covered the concept of porous material quantities. Before defining the quantities, we described the representative elementary volume, REV, and then based on that, we started to say that we have now porosity as the first quantity to quantify the property of a porous material, and then permeability. And permeability concept comes from Darcy's experiment. It is how easy and convenient the flow is happening through the porous rock. And the higher the permeability, the more convenient the flow can be. So with that, I'd like to stop recording this first session.